I will start with literally a 5-minute recap on TRFs with our resources, so that if you're not familiar with our resources, you can see how that works. And then we'll go on to Nate, I think, right? And then we go to Aaron, and finally myself again. So the tutorials are designed to be shorter than 2 hours, right? So 2 hours, including all of your questions. So please interrupt us. I'll start then, unless there are any questions already. No.
Maybe first, is there anyone that has any problem setting up the folder structure or getting the example script run? That's cool.
Right. No news is good news in this case. Okay, that's good. So look, this is basically what I showed in the slides earlier on, right? But in a practical way. So this is my folder. This is my CNSP folder. And I have the same 3 folders that you have in your skeleton. So you have all of this stuff. The difference is that, you know, in the data set, I have all of the data because I downloaded all of the stuff which is in there, pre-processed and ready to be shown. Libraries are the same that you have. Tutorials, of course, I have a few more here, but not really. I mean, I have only mine. I don't have Aaron's and Nate's. So if you open, so you should have this starting pack. Let me see on the website. Where is it? If you go to the resource page, then you should have the skeleton, the libraries, the video, and then you have the beginner tutorials, which is what Mick is doing in the other room, and then you have the starter pack here for intermediate tutorial. So I will ask you to download everything that is in this section. So from the starter pack to the evaluation, the banded, and the CCA, it will take just a minute or so. And on the starter pack, if you download it, it's just a couple of scripts. So it's the script you have already in the skeleton, the forward TRF, a small variant of that script, a little variant of that script that analyzes auditory attention data, and in particular, the auditory attention data from Alexander Bertrand and his team. And then we have a backward TRF script. And finally, example 3, I called it, which is a forward TRF that compares multiple data sets in one go, which is basically what I showed in the slides. So if you just copy them in the, if you just copy them in the tutorial folder. So basically, the way these scripts work at the moment is that the first section is always about adding paths. So very necessary and simple. And it's also running EEG lab, which is somewhat unnecessary, but it helps. Like when you run EEG lab, it includes all sorts of paths for libraries that EEG lab uses, such as the topoplot, which is really the only thing that we need in this particular case. But there are other things that we may need in the future. Then we have parameters here that are specific to the experiment. So in theory, if you're analyzing the natural speech data set here, or you want to analyze another data set, you just need to change this, and then you run the code, and the code is the same, but you can analyze the other data set. That's how it works. So and then the things you can change is the bandpass filter range, where if you type 0, it means that it applies no bandpass filter, and the downsampling frequency and so on. Everything that is run then in the pre-processing section. Now, I run the pre-processing already on my machine. So if you haven't done so, I would suggest you run it on at least the two data sets that we said before. So what was it? The natural speech data set and the Dili-Bach data set. I am so embarrassed about this name that I gave at the time, Dili-Bach. And I think Aaron said that it's cool, or Nate said that, I don't know. I'm so embarrassed, but anyway. So I'll just, you know, tucked in here the pre-processing because I ran it already. And then you can just run this section here. Oh, sorry, classic. Haven't run this. So you need to run each of these sections. Like you need to run the parameters, of course. You can skip the pre-processing if you did it already, and then you have to run when you run this. So I'm running the forward TRF. This is what you have already, and it's running the forward temporal response function for each subject. So each dot here on the bottom, on the top left, represents the prediction correlation that was averaged across electrodes and across trials for a participant. And if you want to discuss this, we can talk about that later, of course. But the point is, we are running this for all subjects, and down here you have the plot, the average TRF across subjects. It's a very clean data set because these were young, healthy people listening to natural speech, and you get very strong global field power, which practically represents the variance across electrodes, which approximates the polarization of your brain response on the scalp. And so a big global field power represents the presence of a possibly polarized response. So there is a plus and a minus, and this becomes obvious here because this is global average referenced. And so basically you see a TRF with components at, you know, around 80 milliseconds and around 150 milliseconds anyway. And here you have the prediction correlation accuracies plotted on the scalp. Now, the reason this topography looks strange in the sense that, you know, it's not just over temporal areas, is because this is global average referenced. So you're averaging all of the electrodes signals, and you're subtracting each electrode by the average. And so what happens is that, you know, electrodes that are in visual areas, let's say in visual scalp areas, occipital scalp areas, you're subtracting the average of all electrodes, which includes some auditory area electrode. And so you get these prediction correlations that may be, you know, all over the place. So that's what average referencing can do for prediction correlations. But you can learn how to interpret these ones as well. I prefer mastoid referencing. So if you wanted mastoid referencing, you know, if the dataset has mastoids, which depends, of course, on the dataset, you can just change average with mastoids, and you will get topographies that look more like what I had in my previous studies. So you can do this for this dataset, and then you can comment this line and get the Alice dataset, which is not mine for once. And here you have another plot, which is the same as before. The only difference is that you don't have the topographies because this dataset didn't have a channel location file that I could load easily. So we need to do a little bit more work there to convert it onto something that works for us. So if you don't have the channel location file, it's just going to skip the topography. And as you can see, it takes a few subjects to get some temporal response functions. So don't expect too much from single subjects. And the other thing is, yeah, for you know, the code shows you the prediction correlation that is averaged across electrodes and trials, and this is averaged across electrode trials and subjects. So this is just a demonstration so far, no tutorial. The tutorial will arrive soon. But if you go to, I have a forward TRF for intracranial EEG, but I won't show it because it's not ready. Now the backward TRF is the same. You go on the parameters and you can select these parameters and run it. And then you go onto your temporal response function code. You can skip in the preprocessing because it's the same in this case. The correlations are going to be a bit larger than in the forward TRF. And I'll explain it later, actually. But the point is that when you do the correlation with a backward model, there are two things. One, you're combining all electrodes at once to predict one envelope in this case. And the other thing is that the envelope is a clean signal, while when you predict the EEG signal, the EEG is noisy, and so the predictions correlations are smaller. And for the backward TRF, the plot is a bit different because it's a backward TRF. So the model weights, you can't really study them in a physiological sense. And that's something that one of the papers that Liberty showed, what was it? I can't remember. Heilbronn 2017, I can't remember. So that's discussed there anyway. We can talk about that. But the main point is that, this is the reconstruction correlation for each subject, which you see is around 0.1. There are other metrics that I will describe during my part of the tutorial at the end. So in this case, this is a match versus mismatch metric, which gives results that have a number that is a bit more understandable than these correlations, and is comparable across methodologies. So I'll describe that later. So this is your backward TRF script that you can use also as a blueprint for your studies if you want. And finally, you have your forward TRF comparison script. In this case, I'm just putting as a cell array these 3 data sets, which is what I showed before. So 3 data sets, just the name of the folder. And I say the downsampling I want for that particular data set. Note that the downsampling in this particular code, we tend to keep integer ratios. So if the data set was recorded at 200, we can downsample it at 100 or 50 or 25. If it was recorded at 1028, then we can downsample it just as an integer ratio of that, so 512 and 256 and so on. So that's why there is a difference between these data sets. And then to preprocess says if I want to preprocess this particular data set or not, so the first, the second, and third data set. And then I just run this code, and it's going to do the same thing as the forward TRF script, but it's going to do it for all data sets, and then it's going to plot them one beside the other. Of course, then at the moment it's a relatively quick configuration. So you have the window is pretty large, the TRF window, but the lambdas, there are just few lambdas. So here I have, for example, a wider range of lambdas, and Nate is going to use another range of lambdas, and Aaron is going to use all sorts of lambdas. Anyway, this is the summary of these scripts. Do you have any questions before we start with the actual tutorials? If you do, I'm here. If everything is good, please someone types that everything is good so that we know that you're alive.
Oh.
What?
Hi, Giovanni, I have a question.
Yep.
So you just mentioned that when you downsample from the original sampling rate, it has to be an integral multiple of the original sampling rate, or the original sampling rate has to be an integral multiple of the final downsample sampling rate. Why is that always the case? Is there any harm with downsampling to some other arbitrary number or something else?
So you don't need to have this constraint. This is just in this particular code that I'm using. The reason is that if you have, let's say, a vector with 10 elements, and you want to downsample it by a factor of 2, then one approach could be I just take every second element, or I can take the average of every pair of elements. So then, or I can apply a filtering and do that. There are many ways, but downsampling by an integer ratio is just a little bit easier in certain cases because you can actually get existing data points. While if you downsample by a non-integer ratio, you need to do a sort of interpolation. So you need to filter your data and then to do the downsampling. I mean, you always need to filter your data, but in that case, you're going to have some numbers that don't exist in the original data. It's absolutely fine. You can do it. I tend to use integer ratios because I don't care if it is 64 or 50. It doesn't make a difference to me. It's just that it's just easier. That's how the function downsample works, by the way. So the function resample, for example, of MATLAB, it allows for non-integer ratios, but the resample also applies a filter. So yeah, you can do it, but I prefer to do it this way. It's a personal choice.
Sounds good. Thank you.
All right, then I'll stop sharing. I'll stop waffling, and I'll give it to you, Nate.
Cool. Yeah, let me share my screen. I'll share the whole thing. Okay, so the second tutorial, if you go, so I'm going to be working with this one, evaluating multivariate models. So I'll be addressing actually something Liberty mentioned of figuring out how good your models are doing. And I'm going to be looking at it from a couple of ways, just generally how well does the model do, but also trying to figure out whether or not specific features contribute to the model. And what I'll be working with is the Dili-Bach dataset. I like the name, Joe, just I really do. Okay,
Great
anyway, so yeah, so that's the data set I'll be using. And all of the analysis I'm doing here is on a single subject. Personally, I really do, when you're interested in like how neural tracking or neural responses happen across a large number of subjects, you'll repeat this for these series of steps for all of the subjects and look at average data. But I personally like having tools to look at individual subject data. It's really interesting. You're welcome to vary the subject that you're looking at. There are 20 in this data set. Some of them show better accuracies for predicting EEG than others. Some don't show great models, some do. So you're welcome to change this subject and look at the various subjects and see how it varies across the data set. So I recommend doing that. So I'll just run this. These are the dependencies. I don't know if you've seen this, but when you first start MATLAB, it starts with a specific seed for the random number generator. So I'll just randomize that to start. It'll be relevant when we're looking at how well the model does. So these are the parameters I'm using. So when I make the model, it'll be 0 to 350 milliseconds of lags. Like Joe said, I'm using a different range of lambdas and 64 hertz. A lot of the rest of this is similar to what Giovanni did. So 1 to 8 hertz, the references, and I'm not using all of the trials. They're actually 30, so you're welcome to increase this, but for the sake of time, I'm working with 20. So those are the parameters. I'll set that up and then load the data. Go computer, it takes a little bit. So I'm running this section here. The first thing it does is it loads the stimuli and then the EEG data. So I want to talk about the stimuli a little bit and the way this is set up. Let's take a look. So what this does is it loads this stim structure. Giovanni talked a little bit about the way CND data is formatted. So you can see it directly here. It's got the names of the different variables, and the data actually contains the, for each trial, there are 30 trials in total. I'll be restricting it to 20 later on. So each trial has 7 different features, STIM. So let's take a look at what those features are. So the first 3 are the stimulus envelope, or it's called speech envelope, but it's not actually speech, it's music. I just realized that. Anyway, so it's the envelope, the note onsets, and the pitch vector. And just to get a sense of what, let me just make sure. Yeah, okay. So each feature is along a column of the trial. So I want to just plot the first 3 features so that we can take a look at what it is. Plot stim data. So we'll just take a look at the first trial and the first 3 features. And I'll zoom in a bit here. So the first one is the envelope. You can see, so what this data set is like a melody played on the piano that's taken from a Bach piece. So each time the blue, which is the envelope, increases, that's when a piano note played. The red is when is the onset time of that note. So you can see it peaks at one point and is 0 everywhere else. And then the yellow is varying with the pitch. So Liberty talked about looking at absolute pitch versus relative pitch. In this case, what we're looking at is the absolute pitch, that it's based on MIDI pitch values. As you go higher, you're getting to a higher pitch. Lower is a lower pitch. It's actually within a pretty restrictive range. And you'll notice that these values are not are right around 3. What I do in this cell is I also normalize each of the stimuli so that the root mean square of the values is 1. So that's why everything's sort of right around 3 in this case. And the reason I set it up like this has 2 reasons. The first is when I do the modeling, it'll produce a TRF, and the TRF weights are going to be more similar to each other when the root mean square or the variance of the stimuli are more similar to each other. The second reason is if you have stimuli with very different variances or very different magnitudes, that can be tricky for the regularization step. So I recommend normalizing stimulus magnitudes before doing this type of analysis. So that's what I'm doing here, but I wanted to show you these. So these are the acoustic features. You've got the stimulus envelope, the timing when the notes happen, and the pitch is also an acoustic feature in this case. And then we have 4 what I've labeled as melody index. I'll be using this later, but let's take a look back at the names again. So we've got pitch entropy, pitch surprise, onset entropy, and onset surprise. I want to just take a look at Giovanni's paper from where this comes from. Let me zoom. I'll zoom up to this figure. This is a really nice figure of the stimuli. So we've got these 4 different features. These come from a model called Idiom, which quantifies the information content in notes that happen in the piece based on both a larger corpus of data that it's trained on and shorter term information within the piece. So specifically, we're looking at how unexpected a note is. So that's what we're calling surprise, and how and what entropy. So this is labeled by H. What entropy is how easy it is to expect a note, how variable the possible notes can be in that particular context. And you can look at that based on the pitch information and based on the onset information. So these 4 variables are what we've got here. So 1 to 3 are the acoustic features, 4 to 7 are these more higher level expectation related features that come from that model. So that's the stimulus data set the stimulus we're working with in our model. And this loads the EEG data. I also do have a pre-processing stage. I'll just run this. It's not too different than what Giovanni did. So I don't think I need to talk through this too much. You filter the data, reference it to the mastoids is what we're using. Just a note when you're working with CND data to pay attention to this. The EEG data starts a little bit of time before, the EEG start is a little bit before the stimulus. You can see that in the data itself. So I have to correct for that. The EEG data actually starts at this padding start sample. And I make sure that the EEG data and the stimulus is the same length before you run the TRF analysis. So what we're doing here is cross-validation and testing. So this is just to fit the model. And I'm doing it by leaving out a trial from training it on the rest of the trial. So this includes finding the optimal lambda value. That's what we find here. And then getting the model on that training data and testing it on that left out trial. So that's what this is labeling. So I'll just run this. It can take a little bit of time. We're working with 20 trials. So by the time this is done, we'll have a prediction accuracy. This is forward modeling. I've labeled that, numbered that here is in the MTRF cross-val function. So we're getting a prediction accuracy for each trial. And what I'll be interested in when I do all of this analysis later is the average across channels. So this model is predicting the data based on these stimulus features we've input for every single trial, and then average the prediction accuracy, which is a correlation across the channels. So this will take a little bit. I just wanted to check if anybody has questions so far. Yeah.
Yeah. So I have a question. You said that at one point you're separating the data into training and test data. And then you made a statement like this also includes the evaluation of the regularization parameter, all the hyperparameters basically of the model.
Right.
So is that yet a different step, or like, do you separate the training set again so that you have different set for training the model and fitting the hyperparameter, or is that?
Oh, that is a good question. So specifically what I'm doing is I pick one trial. So that's what I'm iterating over. So I pick one trial, leave that out and train on the rest. And so the approach I'm taking here is I run cross-validation on these training trials to figure out the optimal, well, I'll come back to that for a second. So I fit the model and find the optimal lambda parameter on that training data. So there is sort of it's a two-step process. You run MTRF cross-val that gives you performance for these training trials as a function of lambda. And then I find the optimal lambda from that. I like to, it's fairly standard practice to have your testing data completely left out from all of the training and cross-validation that you do. And you can think of the lambda as sort of another parameter that you're fitting to your model. So that's what I'm doing here. It is kind of two steps that happen before you do testing. Did that answer your question?
Yes, I just wanted to ask, just to make sure that I understood it correctly. So the train TRS basically is, if you use the MTRF cross-val function, that means that there is again the splitting, right? So even from this data, you train it on some and then evaluate it for the number on the other. So it's kind of nested cross-validate, or I don't know if that's the term that you use, but
yeah, you actually did. Yeah, no, thank you for asking that. So what MTRF cross-val does is it splits the data into folds. That's sort of a general term, but by default, it uses the original trials. And then it leaves, so within the training data that you've applied, it leaves each trial out and then fits a model for every possible lambda value, tests that left out trial on each possible lambda value. And so if you, I'll just take a look at stats. So stats is the, so this is the number of lambda values. Yep. So this is the number of lambda values. This is the number of channels. And this first term is the number of folds, but in this case, it's the number of training trials. Remember, we left one out. There were 20 total. And so you get a array of prediction accuracies for each lambda for every single fold. So when I figure out what the optimum is, I'm averaging across channels. That was that third dimension here. And then averaging across folds. That's what I do, the second mean. And then find the optimal lambda as the maximum of that. Does that make sense? Cool. So these are the model weights. You can see that some of them are, I actually can't access the, there we go. The Zoom thing was in the way. So these are the model weights. I won't talk about them too much. You'll see a little bit of different model weights if you run different subjects. I want to jump down to the main interesting part, which is figuring out how well this model did. So we've got a bunch of values. So these are correlations. And I want to know, is this good? One way we can do that is by trying to figure out a null distribution of these correlation values. And there's a function that we are working on putting into the toolbox called mtrf permute. Let me open it. And it does permutation in a couple of different ways that you can specify. Here, what I'm going to do is circular shifting. So I take each stimulus response pair, so response being the EEG data, and I randomly shift the stimulus in a particular direction. So the timing of everything within the stimulus stays the same, but it's completely mismatched from the original EEG data. And if you randomly do that for many times, you'll get a distribution of R values. Let me just run it so that you can see. Right, what I'm doing is 100 iterations. It takes a little bit of time to run. It'll take longer if you work with more iterations. But for each of these iterations, I take the stimuli, randomly shift them in different directions, refit the model, and that'll give us the null distribution. Another possibility that you can do is permuting. So rather than shifting the trials in time, you just reorder which stimulus goes with which response. So that's another way of getting a null distribution. There are different benefits. So if you're working with a small number of trials that are long, I would recommend circular shifting. If you have a lot of trials, especially if they're short, I would recommend permuting. Anyway, that is done. So that outputs a structure with null correlation values and also null error values. Let's take a look at that. Okay, so, right, because I need to average across channels. But yeah, let me average across channels. Figure. Okay, so this one's a little bit skewed, but it's centered right around 0. So what you would expect is when you mismatch the data, on average, the correlation should be roughly 0. And there's some spread in the amount of correlation. So if you're working with lower frequencies, the spread will get larger. And what we want to do then is compare this to the data that we truly have, because we have a bunch of R values. Let's see how that compares. So that's what this next bit does. So I'll plot it first and then talk through what each of these plots mean. So the black is the null distribution we were just looking at. The circle's the median of that null distribution. And I'm plotting the 95 percentile here, the 5 percentile here. So this, with enough iterations, this will end up being roughly Gaussian. So this is like, if you get values above these lines, it's a p-value of 0.005 relative to this null distribution. And these are the dots for each of the trials and the true for each of the true correlations. So to answer the question, how well does this model do? There are a couple of ways you can look at it. So one of them is to compare each of these dots to this null distribution. And if we want to know, is this subject, is the performance better than chance for this subject? One way you can do that is by averaging these true values and seeing where it falls on the null distribution. So that's what I've displayed at the top here in the title. The answer is 0. So none of these iterations fall above the average of this true. You can see it in the data here too. Because we've only done 100 iterations, I can only say that with p less than 0.01 confidence. So if you wanted to be more confident, you would need to work with more iterations. So 1000 for a better confidence. So that's one way of looking at it. But like I mentioned, it's useful then to compare this to lots of other subjects. And you don't necessarily need a bunch of p-values to tell you that. One useful thing is to essentially normalize these true values relative to the subject's null distribution. And that's what I've done here. So each of these dots, I've z-scored relative to the null distribution. I'll just show you the math I've done here. So these are the true values, RAM. I subtract the mean of the null distribution and divide by the standard deviation. So what we're seeing is if it's 2, it's 2 standard deviations above the mean. You can see that most of the points fall that way. These 2 points are probably these ones here. And then, so that you can do for every trial. But another thing you can do is compute a D prime. Giovanni showed that really quickly in his match-mismatch data. So you would compute, so that's what I'm doing down here, so this is a way of computing D prime. It's a distance between the two distributions. So the distance between the true values and the null values, you subtract the means and then get the average of their standard deviations. And so that gives you a distance between these distributions. So 3 is quite good. I've found that subjects that seem to have poorer data fall below 2. I mean, it varies a lot based on the data you're working with and the length of trials as well. So in a way, what Giovanni will talk about with match-mismatch is similar to the circular shifting, but you're restricting yourself to a very specific window size. So the goal, so what's my time like, Giovanni? I'm wondering if so one of the things we've wanted to set up in these tutorials is to make it a bit more interactive. I'm a little bit worried I'm going over time. So I do want you to try this. My intention is you're welcome to copy the code to answer this question, but modify it so that you can answer this question. My question is, how well does, if you go back to the, oh wait, let me go back. So we can make a model of just note onsets. My question is, how well does that perform? Does that perform above chance? So that's what I would like you to address in the exercise. So I'll just quickly talk through this part. So what we've done is looked at how good the entire model performs. Let's see if a specific feature is relevant. So Liberty actually showed this in her talk. I'm going to talk about two different ways of doing this. What Liberty did is leave out features. So specifically, I want to understand if the melodic features significantly contribute to the model. And you can do that by making a new model that doesn't have those melodic features. That's what this is doing. It's just taking the acoustic features. I'm sorry, does anybody have questions so far? Okay. Okay, cool.
There've been a few in the
so-
chats, but we're taking care of those.
Oh, okay. Sorry, I didn't see the chat.
It's all good.
Okay. Cool. So, so one way is to leave out the acoustic features. Another way is to shuffle the values of the expectations. So what this does is similar to what we're talking about with the circular shifting of the full data, but now we want to maintain the same onsets. So those peaks, if we've still got this. So we want to maintain the same peaks, but just mismatch the actual values. So I'm making two different models, and I'll just run this. Let me see if I can. Okay, yeah, thanks for taking care of the questions. Does anybody have other questions so far?
Yeah, I just had one question with regards to the feature preprocessing. I saw that you had a line which tried to convert all the features to Unity RMS.
Yes.
And I was wondering, how does that differ when you just do the usual mean variance normalization, zero mean and single unity variance? So how does that compare with the RMS unity variance?
Yeah, that's a really good question. My reason for not wanting to do zero mean is because we're dealing with a lot of these peaky onset type vectors. So if you do zero mean, you'll shift all of this down. And I want to make sure that when the model is fitting to the data, that when it's zero, it's not contributing anything to the EEG. And so if I'm dealing with onset type vectors, I would actually normalize a little bit differently. I normalize using the RMS. The envelope also is strictly positive. So unless you normalize it like with dB, convert it to dB or something, normalizing the RMS, I think, is effective. Yeah, that's a good question. Thanks.
Thank you.
So what I'm doing here is fitting two models. So this takes a little bit longer. But what I want to show when this is done is the comparison between each of these models. So when we've left out features in some of these models and made the expectation features in the other one mismatched. And so the goal then is to see how does that reduced model compare to the original true values. And same here, how does the reduced shuffled version compare to the true values? So when that's done, we'll be looking at that comparison. So our goal is that when you've included the expectation values, what we hope is that that significantly contributes to the model. So this should be on average positive, this difference, AM, the correlation for the full minus the reduced. So that's what we'll be looking at in a little bit. Yeah, it's one of those, when you work with more trials, it takes longer. But does anybody have any other questions? Okay. So, and so here we go, great. So it varies across subjects when we look at this. But what we hope is that AM is greater than A, and we're actually seeing that here. So on average, the AM model performs better than A for this subject. If you look at the shuffled values, you see that as well. In practice, what I've found is that actually the shuffled value tends to do a little bit worse than just removing the features. And so that we're kind of seeing that here. I think it's because you're keeping the number of features, but mismatching, like they're completely unuseful. And so that's something that's worth looking at, is also just the reduced model, but when you've shuffled the features. So I don't want to take up too much more time, but I recommend, I have another exercise to run the same type of analysis, but look at, does the absolute pitch values, which were these yellow ones, do those absolute pitch values significantly contribute to the acoustic model? So when you get to these exercises, feel free to email me or message on Slack, and I can address questions. And maybe at the end, we can address questions later. I want Aaron to come in. So what he's going to talk about is when you have all these multivariate features, some of them contribute more than others, and some of them have different frequency content than others. So I could have labeled the phrase starts of these, which are much less frequent than these note onsets. And when you do that, you have to think about how regularization affects things. So I am going to stop sharing and let Aaron take it away.
Thanks, Nate. Everyone see my MATLAB screen? Everyone hear me?
Yes.
Awesome. So I'll be going over the script that is in this link, banded ridge regression. And I'll be talking to you about a little bit about how to do multivariate analysis. This is a brand new function that we have in the MTRF toolbox. In fact, it's not even uploaded to the Git yet. I'm not sure it's quite done to put into the MTRF toolbox, but it is included in the CNSP libraries. So the first thing I want you to do when you have the script, so there should be two versions of the script. You've got banded ridge tutorial, you have banded ridge tutorial solutions. If you want to cheat, you can go into there. And then you've got this ancillary function or script called construct stem. I would not look at that yet because this includes the answers to a problem that I have. But the first thing I want you to do when you open this script, banded ridge tutorial, is go all the way down to line 226 and set a breakpoint and press run. It'll just stop there when it's ready. It'll load everything up. But mostly what it'll be doing is pre-processing. So it's the same pre-processing script here that Giovanni showed earlier. So I won't go over it at all. I've changed it a little bit so that it works a little bit more fluidly with how I'm choosing subjects. You can choose, so mine's already done. So you can choose a single subject, or you can choose, that should be 19 actually, we don't have 20 subjects. You can choose to do all the subjects, or you can choose to do one. I've got it set up to do one, subject 12, which will give pretty good results. If you restart the script with the same subject selected, you can go and select or change line 67 to say if 0. and then it will just skip the pre-processing and come straight down to the banded ridge section. So first, I want to show a little bit about banded ridge. So this is the equation for banded ridge provided by Alexander Huth and Jack Gallant's group, and we'll go over this a little bit later. But the motivation behind banded ridge is that sometimes when you're presenting a signal and recording EEG, you've got all these different features, and sometimes you concatenate features that are quite different. And you can do this with just regular ridge regression, and Giovanni did this in 2015, and he showed like a significant result. It works just fine, but sometimes you can do a little bit better if you treat these separate features in this joint model as separate features, and you unconstrain the model a little bit. So what this does is, if you have banded ridge regression, or sorry, just regular ridge. Sorry, I'm just checking the chat here to see if this was meant for me. Okay, doesn't look like it. If there's any question, just stop me in the middle of what I'm saying, which would be fine. So X here is your design matrix for your stimuli. So what that means is, here in the previous figure, you've got time on this axis and features on this axis. So time on the X and features on the Y. But X will have time in a column and features in each, I'm sorry, time in rows and features in each column. And so when you do XTX, that's your autocovariance matrix. And you can see that the covariance matrix for the spectrogram is much different than the one for phonetic features. But if we're doing regular ridge regression, we're going to apply the same ridge parameter, lambda, to each of these features. But in banded ridge regression, we're going to apply different ridge parameters to each one. And so here, you've got your autocovariance matrices that correspond to each of these quadrants here. So this is X1TX1, and this is X2TX2. This will be your lambda 1, and this will be your lambda 2. And when you do this, it will spit out 2 TRFs. This TRF here, if you do regular cross-validation, it will still spit out all of the appropriate weights, but they won't be banded together. And Jack Gallant and Alex Huth's group showed that when we use ridge versus banded ridge, the banded ridge will typically do better. They did this on an fMRI data set that included annotation. Subjects were watching videos, and they measured the motion in each frame, and that would be one of their features. And they also annotated the video with semantic vectors, and that would be the other vector. So your code should be down to line 226, and I think mine has left. So I'm going to rerun it. It should be pretty quick. So it's down here now. The first thing that you'll need to do is to construct a set of joint feature models. So if I look here in STEM, we have stem.data, and that includes a 4x20. This is your M by N earlier. 20 is the number of trials or stimuli, and 4 is the number of features. Time is on, so this will be the first trial, the second trial, third trial, etc. So time is on the first dimension, and your number of features on the second dimension. This will be your envelope. This is a word onset. These two are both univariate features. This is a spectrogram that includes 16 bands, and this is a set of phonetic feature that includes 19 phonetic features. So I want you to construct a couple of models here. At least construct an EO model, so envelope plus word onset model, and an SF model, a spectrogram and phonetic feature model. And all those will be is this time dimension by 2 for these two models together, or this one will be time dimension by 35. And then a third model that you could play around with is S, F, and O, which will be a 36 dimension feature. If you get stuck with that, yes, please slow me down if you need to. I'll try to wait for a significant amount of time here, but I've got a script that I provided that will give a few solutions to this. I'm just going to run that now so you can see what the stem should look like. So now stem data has 7 by 20, and also don't forget the stem.names has the models added. I've changed the names to just a first letter for ease. You don't have to do that. But this is what stem.data now looks like. Same time dimension and 2 features, where one is this one and one is that one. This one is this concatenated with that, and then this is these 3 concatenated together. So I'll give you a minute to do that. And this will be a good time for questions if anyone has any questions. I just realized I was going without having my video on. Sorry for people who need to read lips. I guess this will be a good time for me to catch up with the chat.
Yeah, there were a couple. Sorry, there were a couple of topics on the discussion on the chat, Aaron, not related to the particular presentation for now. So, but yeah, let us know. It's hard for us to know how this is going from your end because we don't see your video and we don't hear you. So, if this is too fast, too slow, let us know. But it's good to have a little break every now and then, anyway.
Yeah. Is anyone finding so I've given an example here actually that you can copy and basically hard code it. You can just use this line a few times, sorry, this line and this line a few times to get your feature 5, 6, and 7. I'm showing 5 here. Is anyone still working on that? Wow, y'all are smart. So I'll show you a couple of solutions that I came up with. The first is the same way that I just described here, would be to use these lines in a loop, and it looks like this. So for each one, you need to define the first feature and concatenate it with the second feature or third feature, as this one is, and you'll also need to concatenate the names. And so you just do this in one loop and it will update. This should be possible to do in Accelerate, but I didn't get there. Maybe you can. And a more adaptable and modular solution that I came up with is to first construct a series of models. So here's my series of new models, which would be dimensions 1 and 2, dimensions 3 and 4, and dimensions 3, 4, and 2. And then loop through the models and also the trials, but again, you might be able to do this with Accelerate and concatenate the appropriate features together from those models. So now that all of those are done, we can move on and do some banded ridge. Before we do banded ridge, I'll just do regular cross-validation. So put a breakpoint at line 290 and continue until you get there. And what you should see on your screen is the results coming in for the subject for each of the models. So you see the envelope model has a prediction score of this. It does fairly okay. The onset model does not do well at all. Spectrogram does better than the envelope model, and the phonetic feature model does better yet. Importantly, related to Giovanni and his work, the SF model does show an improvement over S plus F. And so this gives us a baseline to look against when we do banded ridge. So the first thing I want to look at is, did any of these models come up against our limits on lambda? It turns out one of them did, but and so if you think this is important, you can adjust the lambdas here. So I provided a couple of ranges of lambda here, and I'm using this one. So you might change the lambda range to be something larger. I am not going to do that because I know that this isn't going to matter later on. And one of the ways I know it's not going to matter later on is if you look at E, the lambda that was optimal is 1. If you look at O, the lambda that optimal is 10 to the 8th. But if you look at EO, it's favoring the E model. And I know that it's not going to matter when we come to it, but you might want to know how to do that. And so that's how you can do it. You might just choose 10 there and run it. You could also change the Tmin and Tmax. You might want to look at earlier, like more acoustic, low level time lags, or you might want to look at later time lags to see higher level processing. That's one way that we can look at low versus high level processing. But once we're down here, we're going to do the banded ridge regression. And the one thing that banded ridge requires beyond
Is it just me or I can't hear anything? Aaron? Hello, Aaron? I can't hear you. Let's take this as a little break, maybe.
What about now?
Yeah.
Where did I leave off at?
You were highlighting that part. I don't remember, sorry.
Is everyone down to here? Is that, should I just describe the grouping variable again? Did anyone get anything on the grouping variable?
You were just starting to talk about the grouping variable and the effect on the combination of features.
Okay, so sorry about that. The one thing that the banded function requires is this grouping variable, and that's just going to tell the function which bands the features go into. So the first model we're going to look at is an EO model, the envelope and the onset model, and there's 2 univariate features. And so this grouping variable has a size of 2 in one of the dimensions. One of them is for the envelope, and the other is for the word onset vector. And they're different here because they belong in separate bands. If we were to do something like this, where it's just 2 1s, that would be the normal ridge solution. So we'll put it as 1 and 2. I'm going to highlight this. Actually, I'm going to set a breakpoint at 307 and continue.
Just a very quick question. So if I have got more dimensional stimuli, for example, or features, then I would put like 1, 1, 1, 2, 2, 2 if I have 2 3-dimensional.
That's a spoiler. So we have a
sorry.
problem later. It's all good.
Okay.
It seems like you'll get that one just fine, but that's the next step, is to construct a grouping variable, or actually not the next step, but it'll be in 2 steps, is to construct a grouping variable for something of larger size. While this is working, you might want to think about how to calculate the optimal lambda combination and extract the best prediction. I'll give you a hint. And really, this isn't that great of an exercise. I put this in here and just didn't realize how little it would help. But you can basically copy this code here, line 271 through 275, with some changes. And if you have problems with those changes, let me know. How do you hide? Nope. There it is. What did I do? Oh. Anyway, so that was an error that is because there is no grouping. So just ignore that. So once this is done, I had it plot the results. The output of banded ridge, and this will help you in the next problem, is this structure called stats. Let me put this back up so you can see the pretty picture. In stats, you've got the normal correlation coefficient and mean squared error. The middle variable, or the middle dimension, is the lambdas, and these are not the original lambdas as they were given to the banded script like this, but they are a matrix. They correspond to this dimension in a matrix of lambda that describe each feature, which lambda they receive. So if 1 is the best lambda, the first feature received 10 to the minus 4. The second feature received 10 to the minus 4. In this case, you will find that the best feature is number 19, I think. That might have been from a different participant, actually. So what I'm going to do is I'm going to figure out the best lambda here. I lambda is 24. So the best lambdas are actually 1 and 100. So a value of 1 for the envelope and 100 for the onset. Does anybody not have the extraction and of the best predictions? If not, I will just copy and make the appropriate changes here, and you can follow along on your machine. So the first line is essentially the same. It will just output which index of the lambda by features matrix, and the max R will output the maximum correlation. But since the lambdas, you're going to have multiple lambdas, 1 for each feature, the original lambdas variable isn't going to work. So we use stats.lambda. And so when we output this, we see that that is, I'm sorry, we need to specify the second dimension too. We see that here's the 1 and the 100. And so that will not fit into this that we had before. And because we're going to be doing multiple models with different numbers of features, it won't fit in a double precision array. So I just changed this to be a cell array. And so in this cell array, And if we want to change this to banded, so that we save everything appropriately. So in this cell array, the size of this can vary across different models. So we'll just execute that as well. Cool, that didn't work, but the fprintf part is not important. Oh, that's just because it's a cell array here. And finally, you will need a second %G sign because there will be two best lambdas here. Now we'll re-execute that, and we see there's the R value for banded lambda. So here's a visualization of what happened. Along this dimension is a set of tuning functions for the feature envelope feature. And along this dimension is a set of tuning functions for the onset feature. And you'll see that across most of the onset features, the envelope feature is varying quite substantially, and the O feature is not really varying that much. We do get a little bit of boost from banded ridge, or at least the solution is not the same as the ridge solution. So along this diagonal represents the ridge solution. So really high, it's where lambda for feature E and lambda for feature O are the same. And so this will be your regular ridge solution, and this will be the banded ridge solution. Okay. Next thing to do is construct an SF model. So here we have two multivariate features. The first has 16 variates and the second has 19 variates. So you're going to have a model that has a total of 35 features. You need to construct the grouping for that. And I'll give you a minute or two to do so. Specifically, we want the S model and the F model to be in different bands. So you do need 1s and 2s in here. If you could just let me know when you're finished with that, by like a hand or some sort of reaction. And I'm not seeing any hands to show that people are done. So is anyone having any trouble like understanding what this grouping variable should look like? Cool. I guess I should have mentioned here the color represents the prediction correlations. So between this blue to the green to the orange to the yellow, that's an increase in prediction correlation. And so when I say that there's a bit more variability across feature E, that means it's going from blue to yellow, as opposed to feature O. Most of the tuning functions are like within yellow to yellow.
I have a question, like a more general question. I mean, choosing the best lambda here, you now worked with the maximal correlation, right?
Right.
But sometimes you also use the minimum error between the predicted and the actual signal.
Right.
Why would you, or when would you use the one or the other? Or if you have two different solutions, basically the one gives you a lambda of 1 and the other one of 100, do you then take 10, or like how do you go about this?
So the idea behind banded ridge is that you would use both lambdas. So we don't have a predict and train function that will use 2 different lambdas. I think that's something that I will probably work on next. But the idea would be that if you're fitting a TRF for O, you would use the lambda for O. If you're fitting a TRF for E, you would use the lambda for E. So you wouldn't want to go in between. But that's sort of what the regular ridge solution does. Here, the regular ridge found the best lambda to be 1 or 10 to the 8th. And when done together, the best lambda was actually 100. So it kind of goes in between. Funny that the banded solution was 100. Sometimes when you include 2 features together, one will absorb all the variance. So part of what is going on here is that E is absorbing all of the variance for O. And so that's why O isn't varying that much across different lambda. What was the first part of your question? I know I wanted to answer that second, but I forgot it now.
So basically, when do you use the prediction accuracy and the
Oh, right.
correlation, and when do you use the error? Oh,
So the correlation and the error will like give you 2 different measures of like how well the model is doing. So error really cares about the magnitude of your predictions. So if you're predicting generally the correct trajectory of the EEG, but it's in the wrong magnitude, and sometimes it can be because of the regularization, then the MSE will give you weird results, and it won't vary enough across different lambdas, I think. But the correlation coefficient will take that into account. And so if you have an actual EEG signal that varies quite a bit, and then a predicted EEG signal that doesn't vary that much, but still follows the correct trajectory, the R will like give you, a measure of that. But if you're interested in getting the actual scaled values of the EEG, then error is probably better.
thank you.
Welcome. All right, so now we'll move on. In case anyone didn't get this, I will copy this from the solution because I don't remember the dimensionality. If it should be the number of features, then 1. Nope, it is 1 and then the number of features. So here's the solution to the grouping. I'm just going to use the function ones and have 16 of those ones, and then ones and have 19 of those ones and multiply it by 2. So this will give us a 1 by 35 matrix that looks like so. We got ones up into feature 16 and then 2s after that. And I will highlight these and execute them. While that's running, you can do this part, which is literally just copy and paste here. And also you might, while this is running, you can figure out the grouping parameter for our next model, which will be 2 multivariate and 1 univariate features. So you've got your spectrogram here, you've got your phonetic features here, and you've got the envelope, sorry, the word onset model here. So we want to construct a grouping variable that will group all 3 of these into different bands. So you'll need a 1 for this, 2 for this, and a 3 for that. Is everyone keeping up with the tutorial just fine? Cool.
I just have a question about visualizing this plot when you combine more than 3 feature sets. How would you visualize that?
I'm sorry, say this again.
Yeah, so I just see this matrix over here, right? So you have a lambda value for each and every feature set.
Yep.
So how do you visualize that for more than 3 feature sets, right? So
You just do the same thing. And I'll show you that. So the first thing that you would have to do is to construct the appropriate models. So if I wanted a model to be, if I wanted a different model, I might want a something like this, where I include all 4 features together. And what that will do is in your stem variable, you will have an 8th one, and it will be 37, right? Then when you decide on the grouping, just like we started off with 1 and 2 here, and then we have a bunch of 1s and a bunch of 2s here for 2 feature models. Here, you're going to do something to make it a 3 feature model. And you can just keep doing that to make it a 4, a 5, a 6, or a 7 feature model. I will say that when you get beyond 2 feature models, especially if they're multivariate features like these, it will take a long time, because here so in regular ridge regression, it will have to do however many lambdas you have. So I think the number of lambdas here are 7. And I have deleted something in here. Yes, okay. When you do a 2 feature banded, it will do the number of lambdas raised to the number of bands. So that's why in this stats, it is 49. If you were to do 3 feature, it is again number of lambdas to the number of bands, so 7 to the 3rd power or 7 to the 4th power. So every time you add an extra band, you add an extra power of how many lambdas you are, and the computational time explodes. I started off this function with a version that does like optimized search. It was way too overboard for 2 feature models, but it might be appropriate for higher number of feature models. So we'll probably put that out also. So this SF model is finished, and I will show you the 2 different models. So here we have the EO model, Heyo. And like I said, the O model doesn't really contribute much because it's the red here, its tuning curve is very flat. But if you look at the SF model, both of the tuning curves for that, and so these tuning curves are just intersecting the banded ridge solution. So the S model is this row here, the S model is this column here, and that's what you see here in blue and in red. So you'll notice, first of all, that the solution for those are different, and neither of them are as flat as the O model. So that is an indication that both of them are contributing some. It's a recapitulation of Giovanni's findings that they both share some unique contribution to the EEG. And importantly, the banded solution is more different here than it is with the EO model. And so what the script will go through, if you end up running on all subjects, it will record these lambda values. So first it will record the ridge solution and its value. and it will record the banded ridge solution and its value. And you can have a look and compare between within an individual the ridge solution and the banded ridge solution. And you can do the same thing. I won't do it here, but I will give you the solution. Is anyone not done with this grouping solution and want to? It's pretty easy. It's just a copy and paste there and the 3. That's it. So with this grouping solution, or grouping variable, you can then run the last model, which is spectrogram, phonetic feature, and onset model. I'm not going to do it now because it takes too long, and I can't plot it because this plotting function only handles 2 dimensions or 2 features at a time. But hopefully this gives you an idea about banded ridge, the importance of regularizing features separately, or maybe not the importance of doing it, but the benefit of doing it if you need to. Like I said earlier, Giovanni did his 2015 paper without banded ridge, and it does just fine. It finds an intermediate intermediate lambda value in most most cases, which is sufficient. But this is just a way to give yourself a little bit of extra juice, especially if you have features that are drastically different in terms of like its frequency content or its type. So like, for example, the feature model is a stick model. It's all zeros, but with 1s on the onset, or 1s when there's a phonetic feature present. And this spectrogram model is a continuous model. There's always a value going. So those different kinds of models might take different kinds of regularization. And so with that, I'll leave it up to questions. And if there are no questions, I'll let Giovanni take over.
Yeah, I just have one single question.
Yes,
so would you also recommend applying Unity RMS preprocessing to all the features, just as Nat just mentioned?
I'm sorry, what kind of preprocessing?
So when you have a bunch of features, right, would you convert them to Unity RMS before you feed them into banded ridge?
So I did not normalize the features. You're asking about dividing by the RMS. So I did not do that for the stick models. It might be useful to do that if you're doing the regular ridge solution, because you want to have all of them in the same like value space or like around the same value. But here, since we're treating all the features differently, it's not necessary. So in my models, the continuous features are divided by their RMS. The stick features are not at all. They're all 0s and 1s. Yeah, so I forgot to mention that it's not necessary to normalize the different kinds of models in the same way. Yeah.
Thank you.
All right, with that, I'll turn it over to Giovanni. Thanks for your time.
That was great. Thank you, Aaron. It's, there's more and more people working on multivariate models now. And, ideally, when you have lots of data, then banded is the, sorry, these are, okay. Ideally, if you have enough data, banded is the best solution you can go for. The tricky part is when you don't have enough data to run proper, you can't get reliable R values to run your banded, and then you're forced to go for those normalizations or tricks that, as I was doing at the start. But if you have enough data, like on those data sets we shared, then banded is the way to go, I think. So thanks a million. Everyone is tired, I suppose. We're the last half an hour. We have 21 people in the call. We lost a few people. It happens. Is everyone still here? Can you give me a shout if you're still here? Raise your hand or something. I can see the ones on the video. Oh yeah, I see Dana is there. Okay, thank God. We don't know what happens. We don't know. We just see a black screen, so we have no clue. Is it going well or not? I don't know. Okay, so I'll try to be to the point. Meanwhile, you can keep asking questions. I saw like there is a nice discussion going on in the chat, a parallel discussion, so that's cool. So my presentation is about CCA, right? So first of all, actually, before I start waffling, does anyone know? Has anyone ever worked with CCA or read a paper about CCA, or do you have a clue what it is about? I see a few hands there. Okay, what does it mean?
I have read Alam's paper, so yeah.
Okay, I see Aaron. Aaron, have you worked with CCA?
I've tried. I've done a little bit, but it's like magic to me. So I don't quite understand it. So I'm really looking forward to it not becoming magic anymore.
Okay, and I know the Sarah and Amir haven't yet, but let me give. I see on the chat is still unbounded. So let me go back to the screen sharing. So let me give you really a 5-minute explanation of what I'm talking about here. Let's see. You can see the screen, yeah?
Yep.
Grand. Oh, now CCA. Now I learned this. This is like I didn't make this up, right? This stuff existed for years, for decades. And then Alain de Chevenier, one of my mentors, he started working with this when he was working on the cocktail party decoding. The project was called Cocoa Project. It was a fancy, big collaboration between universities and the company, Oticon, Ericsson Research Center, to try to get an actual device that can figure out which person you're attending to and decode that in real time and steer increase the volume of the person you're listening to. And it works. It's just super slow. Anyway, CCA was the way we chose. It is slow, like to the point that you need 7-8 seconds to figure it out. And that was the best we could ever achieve. Like you can go down to 3 seconds, but then it becomes really unreliable. So, but I'll talk about that. So now this is the forward model, the backward model. This is a plot from Alain that gives the idea, you take your stimulus and you project it to the space of the EEG. That's what you're doing. You're trying to predict the EEG with forward models. You can consider that a projection. We also call it the rotation. It depends on the field you're in. Anyway, backward model is the same thing. And you're taking your EEG, you're rotating that onto the stimulus space. And then you calculate your correlation here, your raw, which is your correlation between your reconstruction and the original. So this is, you can see this as a projection onto the stimulus space. Now, CCA is doing what I said before. So you take both your stimulus and your EEG and you project both of them. So the projection is a bit like what you do with PCA, ICA. You may be familiar with ICA because of data preprocessing and things. So it is just a multiplication by a matrix. So you're taking all of your electrodes and you're finding a linear combination of these electrodes, so a weighted average of these electrodes that gives you something that is most relevant as possible. Relevant depends on the algorithm you use. If you use PCA, relevant means the maximum variance. So that projection, the first component of PCA, explains the most variance that you can, basically, of the original data across dimensions. So ICA is independence. Here instead is correlation between the input and between the A and B. So between your stimulus and your EEG. So instead of having just one W matrix like in the forward model or one G matrix like in the backward model, which here are called differently, they're called V and U. You have 2 projections. So you're taking all of your stimulus and you're projecting it onto a space that is most relevant to the EEG. And then you're projecting the EEG onto a space that is most relevant to the stimulus. And you do this, and the first component is it's a pair of components, is one for the EEG and one for the stimulus, that is maximally correlated. So you multiply your stimulus by this matrix, and you multiply your EEG by this matrix, and the first component has the maximum correlation you can ever get with a linear transformation. Then you remove that and you have the second component, which is the maximum correlation you can get after removing the first component, and so on. So the bias function here, the goal, if you want, of CCA is to get the maximum correlation. Is correlation relevant? Well, it is more relevant than variance, because in EEG, lots of the variance is irrelevant to our goals. Well, so it is relevant, but now you're calculating correlations in this space, which is not the EEG space and it's not the stimulus space. And so what the hell is this correlation, and what do you do with that? So anyway, there are different ways of running CCA. I'll drive you through that. Mainly it's the idea of, do I apply time lags to the stimulus? Do I apply time lags to the EEG? Do I apply time lags to both? Do I apply something else than time lags? And this is a trick that Alain was using, this filtering, which was creating a smaller, it's a filter bank that was kind of replacing the shift, these time lags, but with less dimensions. Because with time lags, if you apply 10 time lags, you have 10 dimensions. If you apply 100, you have 100 dimensions. With the filters, you can, you can get lots of the information with less dimensions. And here on the right, you see, like, if you calculate the D prime measure, and I'll explain that in a minute, the backward model is a bit better than the forward model because you're combining all electrodes at once, and then you get CCA for the single best component, which is this one, and then this joint CCA with all components or multiple components, and you get something that is better. So this just tells you how good it is, and the duration, I'll explain it in a second. So this is the first example that we'll see in the tutorial. So basically, you get your stimulus and you get your EEG, and you run CCA on those two. And it's not a great way to run this, especially if your stimulus is the envelope, because basically the envelope has one dimension, right? And as component analysis, in this case, is going to project your data onto a space that has the smallest of the two sizes. So if the EEG has 64 channels and this envelope has just one dimension, you just get one component. If you had a spectrum with 2 dimensions, then you'll get 2 components. If you have a spectrum with 16 dimensions, you get 16 components. So you get the smallest of the two, or the 64 and of whatever dimension you have in the stimulus. So why is this not a problem? Because usually we apply time lags. So when you apply time lags, the envelope is not one-dimensional anymore. And so, but you need to remember, it's important that you consider how many dimensions you have on one and on the other, because that's going to impact your result. And note that you can also use this for denoising, by the way. So for example, you can take the EEG and the stimulus, you build the CCA model, you go onto CCA space, you remove the really irrelevant components, the last components, and then you can project back to the EEG, and you get an EEG signal that is denoised, that just has the component, the signal that is relevant to the stimulus. But I won't go that far. Anyway, the approach I use generally is I apply time lags to the envelope. Then I run a PCA, because maybe I got too many dimensions. So you apply the PCA to reduce the dimensionality of this thing, and you apply PCA to the EEG to reduce the dimensionality of the EEG, and then you run CCA. So you understand that it's much more complicated than the TRF. The TRF, you just run it and you have one parameter. Here you have, how do you time lag the stimulus, do you time lag the EEG? Then you have another choice, which is how many PCs do you keep here and do you keep on the EEG? How many components do you keep for CCA? So it's more complicated. You don't run it on small data sets, you need to run it on bigger data sets. And it takes a long time, but it is better than TRFs. So you can also do this, you can apply time lags on both sides. And finally, you also have, so Alain has this thing that he calls shifts, and that is in its function. So you can just shift the stimulus and the EEG. And so in the simplest case, where you just run the envelope and the EEG, where you just, the case I said before, where you just have a one-dimensional envelope. So your CCA is just going to give you one component. It's practically a backward model. It's the same as backward model. And the only thing that you do is that you shift, you run this for many different shifts between stimulus and EEG, and you get your correlation. So it's really the same. It's comparable with the backward model in this case, and that's the simplest case. But you can augment then the envelope to get all of these other dimensions. Go for it. Questions?
Yes, I remember we discussed this paper in our journal club, and we were wondering about this time lag. If it's in second, like normally when you look at TRFs, it's like within milliseconds, let's say 100 or maybe 300 milliseconds. So is that a different kind of shift that we're seeing here? Or why is it about like 1 second?
So with temporal response functions, we generally, and I say generally because I don't always do it, we generally filter the data, around from 1 to 8 hertz, from 1 to 15 hertz. Alan doesn't like filtering at all. You must have seen his neuron paper 2019, I think. So he doesn't like filtering because he's aware of the issues that come with filtering, such as filtering artifacts. Now, CCA is a filter. A rotation and transformation is the same as a filter in terms of efficiency. So if you give this thing the raw data or minimally processed data, or you keep the low frequencies, the CCA is going to give you components that are taking some frequencies that are more or less relevant. So if you run this with TRFs, it's a mess, because the TRF is just going to be like a smooth stuff that you can't study really. And you can do it. There are ways, but generally, if you want to see a TRF like an ERP, then you filter it above 1 hertz. So here Alan is using low frequencies. When you include low frequencies, there is strong serial correlation in your data, especially when you get this kind of speech and music data, especially. And so what you see here, if you see a peak at 1 second, it doesn't mean that the most relevant thing is at 1 second. It also denotes a certain serial correlation within the data that causes this massive smoothing. So it's really hard to study this thing as a TRF. So in TRFs, we call it single lag analysis. But single lag analysis shouldn't be studied like TRFs in general, or like ERPs, because they are not considering the autocovariance of your matrix. So they are not considering this serial correlation. I'm sorry, it's an elaborate answer. I'm just saying in this case, it's using very low frequencies. You get large serial correlation, and what matters, may be different from what you're used to see. Sorry, I'm taking a long time. So the point is, it's hard to deal with correlations in this case, because the correlation is not comparable to what we were using for TRFs. So one approach is the match versus mismatch classification metric. With match versus mismatch just means that you, for example, predict, you fit the CCA, and with the stimulus and the EEG, and then you take some random portion of the stimulus, you rerun your CCA, and you see whether the correlation between the first component, is higher for the good stimulus or for the random stimulus. If it is higher for the real actual stimulus, then you have a correct classification for that particular chunk of data. So it's like the cocktail party in a way. You're trying to figure out, is this the right portion of the data that corresponds to this EEG? And of course, you can do it for chunks of data of different size. So if you can take 30 seconds of data, and you can say, oh, do these 30 seconds correspond to the stimulus that we care about? Or maybe they correspond more to a random stimulus. In that case, the model is not working. But if you take 30 seconds, you usually have a better chance to get the correct classification than getting 3 seconds. So the smaller the data, the more noisy, the less accurate your prediction will be. But the good thing is that you can do this kind of match versus mismatch classification on CCA, on TRF for a model, on TRF backward model. And you can say, okay, when I get the, in this case, you can get your correlation for your CC, for your first CC. This is from, I think it's from the Old Man and the Sea dataset, the natural speech dataset. So you get, for the first component, you get correlations of 0.3 that are ECOG level, let's say. A correlation of 0.3, you never see it with TRFs, right? And then, but what does that mean in terms of match versus mismatch? Is it really better than TRFs? And then you have to say, okay, with 30-second window, you can say, I can get on subject 6, I get a 76% classification accuracy or whatever. And then you can plot these things where on the left-hand side, you have correlations for individual subjects for different shifts, what you were asking before, right? So in this case, the optimal shift, because I'm filtering the data like with TRFs in this case, you see that the optimal shift is at, I don't know, 100 milliseconds or something like that. But you see correlations go up to 0.35, unseen, never seen with TRFs. Depends how you filter it, of course. The match versus mismatch with 30 seconds, like you get certain subject where it's 100%. So with 30 seconds of data, you always know, okay, this EEG chunk corresponds to that piece, to that portion of data. So that's what the match versus mismatch means.
I have a question here. Does each color correspond to a different subject?
Yes. Yes.
Thank you.
So it's just on this data. Yeah, you can try it on any data set. Anyway, the tutorial I'll show you now is the same thing as before. I include the libraries, initialize the parameters, run the pre-processing, which you don't need to run if you have run it before, but you can run it for one subject now if you want. And then the CCA and the plot. Are there any questions on the concept of CCA? I mean, I think it's well represented by...
Joe, actually, can I ask a question?
Yeah.
I was looking, I wanted to, can you go back to the slide with the correlations and match mismatch?
Which one?
It was like the second to last slide, that one, yes. I was wondering, this one. I was wondering why the correlations look sort of smoother for each subject as a function of shift versus the match mismatch. I was wondering if you could talk about why that is.
It's a good point. I've never thought about that.
Okay.
Well, that also gives you an idea of what meaningful means. So having a high correlation doesn't necessarily mean that it's meaningful to your goal. So if you go to a shift that gives you a lower correlation, it may be high correlation because you're capturing something that is, there is serial correlation in the data. You know what I mean? So the data has certain regularities that are always going to be there. If you get the wrong shift, you're still going to get some correlation, but maybe that's not sufficient to then say, oh, this is the right piece of data versus the other. So the match versus mismatch is sharper in that it tells you what is meaningful rather than what is correlated.
Okay.
So when you run the evaluation also, I think when you run the permutations and everything, you can sometimes get correlations that are above 0 and everything, but that doesn't necessarily mean a correlation that is close to 0 but still above 0 with a shuffle stimulus. It could be meaningful because maybe there are some correlations in the stimulus. With music, for example, maybe two pieces have the same tempo, but it may be completely meaningless and it's due to some serial correlation. So it wouldn't maybe be good at doing the match versus mismatch. I suppose that's one of the points of Alan in using match versus mismatch. Yeah, sometimes you see it in the form of D prime, but in this case it's a classification, but it's the same thing.
Oh yeah, I have just a follow-up question on that. So for the mismatch or match classification task, in the plot here, did they use only the first canonical correlation, or did they combine a few CCs?
Yeah, so in this plot I used 3 CCs. So that's one other. So that's a great question, because on the correlations, how do you combine different components? Do you average their correlation? Does that make any sense? Not really, because maybe component 2 has a lower correlation, but it carries extra meaning. So it's hard. So with the match versus mismatch, that's also maybe another answer to your question, Nate. It's a great point. that in the left plot is one component, the right plot is 3 components combined for the classification. You could use as many as you want.
I guess okay, so I'm wondering if for each of those shifts, if you're doing match versus mismatch again, like a new time, and that's something that came up in the chat when I was talking about permutations. Like I was only working with 100 permutations, and I was kind of surprised to see that it was slightly skewed. But that can kind of happen by chance, and like it didn't happen very often that it was like had a bunch of negative values. So if you're the match versus mismatch adds randomization, and that's I guess what I was wondering about is like if that's why it looks noisier.
Yeah, and Sarah, who is in the call, Sarah is a PhD student with me, so she was having the same problem today. Actually, we were talking about that, about, you know, you do the permutations and you still get some positive correlations, and you're like, okay, what do I do with this? And yes, in this case, you add some randomization, plus you need to remember though, what are we shuffling here? What does it mean? Like if it was music, for example, can we actually do a match versus mismatch completely random? You know, we need to be careful about the chunk size, because maybe we are chunking at the time at the size of the tempo. So we need to be careful about how we randomize and what that means. I'm sorry, I'm going longer than I expected. If you're all still in good shape, if you can open tutorial part 1, I uploaded also the solutions. Did you have problems downloading, or did it work?
There were only the solutions, not the one without the solutions.
I put in the chat a link to the zip file without solutions. I noticed that it wasn't linked on the resources page. Does everyone see that link?
Yeah, I see it in the chat. Thank you, Aaron. Sorry, I messed up between the various
I'm here
things
for you, Joe.
So maybe we won't do exactly everything. Otherwise, I'll keep you here until midnight. And who knows at what time zones you are at. I hope lots of people are from California, because it's a good time for you. It's not a good time for me. I'm really hungry. And so I'll give you another couple of minutes. Have you all downloaded this file? Yeah, grand. Can I see another hand up in the crowd? Yeah, Aaron. Thank you, Aaron. Okay, the love symbol was excessive. You'll hate me after this. So, okay, I run it for you now. I'll clear all so that we are all starting from scratch. Now, this is CCA tutorial part 1. It won't run fully because it's to be completed. Now, as I said, you can be more relaxed in terms of filters here. Now, remember, all the filters that I run are very mild filters. They are Butterworth filter of order 2 or something. It is field, so the order becomes 4, but it's still the mildest as possible. I still apply some filtering with CCA. Alan sometimes just doesn't apply any filtering because it's hardcore in this sense. But I like applying some filtering and just keeping an eye on what the filter is doing to the data. So it's the simplest thing. I am downsampling to 32, and you can even go lower because CCA is just, you can run the preprocessing code in the meantime on one subject. I downsample to 32 because CCA is slow, and so I prefer to go a bit below. So 32 means that I can have a maximum encoded frequency of 16 because of the Nyquist law, of course. So if you go to 16, then you can have maximum 8. So remember that. Otherwise, you'll get aliasing. So imagine that you run the preprocessing for one subject. It doesn't take that long for one subject. Now, this is the data set. What data set is this? Lolar natural speech is the same for all data sets. And there is stimulus index. In this case, I selected the envelope. We need to select our stimulus file name, and then we select our EEG preprocessing file name here. That's the only to do that you should be doing for this part, really. So since it's pretty boring and you've done this already, I'll do it for you by simply opening the solution here. So the stimulus file name is going to be the usual thing that you have in the other scripts. So your main folder, your CND subfolder, and the data stream is the same as before. Same thing for the EEG, stimulus folder, CND subfolder. Now, in this case, I am loading a different preprocessing file so that you don't override the one that you use for TRFs. So if you look at the preprocessing, you should see at the end that I'm saving something called preprocess CCA, just for, so not redo things 1,000 times. But if you run this, what is going to happen is that the code is going to run for every subject. It's going to be fairly fast. And what is this code doing? Exactly what I said before. So you take, you take your XX, so your stimulus matrix, your data matrix for the envelope. And then you take your EEG data, so all trials, just one shift. So we just we don't shift anything. We just take the EEG data and the stimulus synchronized. And then I'll explain that in a second. And then you run your cross-validation for the CCA. So it's the same as MTRF cross-val, but it's running the CCA. And it's a modified script. So this is taken from Alain's original script. I modified it to include the match versus mismatch. And the match versus mismatch is going to be run on, so this is Vishal's question from before, on, in this case, one component. You can run it on 3 components like in my plot from before. You can run it on how many components you want. Let's say that we could just calculate it on one component for now. And it's going to be calculated on this window, so on 5 seconds, for example. So you're going to figure out this classification match versus mismatch on 5 seconds, or if you want on 30 seconds or whatever, as long as it's not longer of your trials. Otherwise, of course, it's not going to work. So the anti-CCA cross-validate is just needs basically the stimulus and the EEG. And your output is going to be a transformation matrix for your stimulus, a transformation matrix for your EEG, which you don't need to use in this particular script, but it's good to have. A correlation between your stimulus and the EEG. And it's going to be a correlation for each component, for each shift and for each trial. So of course, if you average across trials, as we do for the EEG, you're going to get your average correlation. Your average correlation, for example, 0.16. This is going to be your average correlation for the single component you get. Now remember, in this case, your XX, you see, it's just the envelope. So it's one-dimensional. And so as I said before, your output is going to be one-dimensional. So just one canonical component, because you can't get more components than your dimensions. It's mathematically doesn't make sense. Actually, technically, it's more than the rank, the minimum rank of your input, but I won't explain that now. That's the linear algebra. So if you run it, you're going to get, this is already CCA, and there is a lot of text, but what you have to focus on really is this R-all, which is your output, is the correlation between the first component for stimulus and the EEG. And if you plot this, you will get exactly what I had in the slide earlier on. So for subject 1, you get this correlation. For subject 2, you get this correlation. For subject 3, you get this correlation. So I'll leave this to you in terms of the solution of part 1 is what you can run as a basic script. But are there questions here? Otherwise, because then in part 2, there is something to do.
Yeah, I think I have a very quick one. So you always say the correlation between EEG and the envelope. Is it the correlation of the transformed EEG and of the transformed EEG envelope?
Exactly.
Okay. Good.
Exactly. So it is mathematically, I never remember the orientation, but it's basically correlation between, I think it's XX multiplied by AA. Not really, because XX is a cell, but let's say each, cell one of the first trial multiplied by its transform correlated with the first trial correlated by, so multiplied by its transform. So it is, as you said, it is in the transform space. And so the cross-validate is doing it for every trial, blah, blah. And that's also why we don't know what the correlation means. We just know that, okay, we can get a transform that is meaningful in terms of you can get a good correlation, but yeah, it's hard to know. Is it meaningful? Is it better than TRFs or not? We don't know. Now, same thing, if you look at CCA part 2, sorry, I'll just close the preprocessing. So you can do this more slowly, let's say, also in your own time, and then you can also ask us questions. But so here I have some instructions, but this is a slightly...
Preprocessing is the same for all of your parts?
Yes.
Okay, thanks.
So you don't need to rerun the preprocessing. And again, you can run it just on one participant, it's fine. So I just heard that they're still going overtime in the other room as well. So we're not the only ones overtime. So same thing as before. What did I add here? You can see here there is a number of principal components. Now we'll get there. In practice let's go back to the code. So this is again cross-validation, the CCA cross-validation. This is the new code that I added. So we still get our, where is it? We still get our XX, our stimulus, and we still get our YY, our data. Now there is something for you to do. So listen to what I'm saying. It's easy, but I'll still tell you. So this is the T-min and T-max that corresponds to the T-min and T-max of the TRF, for example. So it's the lag window. So in this case, I put it to 0. It could be 0 to 500 milliseconds. It could be whatever you want that we usually do with the TRF. Yes, this is just the step of the lag window, but forget about that. It's just if you want to make it faster, instead of going sample by sample, you can skip samples, but keep this to one. Just think about what is the window you want to use, so that you have to set like you would do with the TRF. This is just code that sets the shifts, and then we run this code. So this is the critical code. It's just one line, but you get your XX, which is at this point, and just stopping it here. Oh. I don't know what this step is. I'll fix it in a second. So, this step is actually this sample step, sorry. So if you stop your code here, you see that X-axis is what we had before, so it's just the envelope for every trial. Now, this function is going to apply the time shifts. So it's what we used to call lag generator, but specific for the CCA. The thing is, it's going to apply these shifts, and then you have maybe lots of dimensions, maybe 100 different dimensions. And then at the end, if you look at the script, it applies PCA. It applies PCA to reduce the dimensionality, which helps reducing the risk for overfitting and so on. So everything you need to know is, I get my envelope, I apply these shifts here, and this is in milliseconds, so 0 to 500 milliseconds or something. And then I keep 10 principal components, 30 principal components. Now, for now, it's an arbitrary decision, but in the end, it's going to become formally identified as Aaron was doing for the bounded regression. So you can do cross-validation and everything to figure out the best hyperparameters. But for now, just pick a number, and the number of principal components is here. And then do the same for the EEG. So this is the EEG data. right? So it has 128 channels, because at the time we were crazy and we were recording 128 channels with the biosemi system, which is actually not necessary for doing this kind of stuff. We just need 64, 32. So what I'm asking you to do is to take this and basically run the same function that I use for the stimulus and select the number of components and successfully run this code. I'll give you a couple of minutes maybe. So these lines, so this one and this one are really the only things to do. Do you have questions? Or if you have any errors that come up, I'm here.
Yeah, so Giovanni, I just have a question that I want to raise. I see that here we are choosing a fixed number of PCs to keep, right, after the PCA. Can we also come up with the criteria, let's say, to retain 95% of the variance and then choose the number of CCs based on that? Is that also a valid approach?
It is. So what I often do is my criteria is to keep the number of channels, as number of dimensions, I keep the number of channels of the EEG. So basically, if I have 64 channels, I augment the 64 by adding the time lag. So I arrive to 600 dimensions, and then I do a PCA to go back to 64. Is it a good criterion? No, it's not. Your criterion is better, but the use variance is not what we really care about here, right? So then you need to be careful, because then variance is going to bias your result by low frequencies. Because of course, low frequencies have higher power. And so you have to be careful what your criterion is. One solution is to find it, not manually, but with a grid search. So you have a validation set and you just try a number of values and you select the optimal value based on your validation set. So in that case, the criterion is what gives me the best match versus mismatch, which is what I think is meaningful in this case. Yeah, there is a number of things, and CCA honestly is complicated. It can be worth it though, especially if you're thinking about real-time applications or improving your decoding or things, because in the end, it's just a multiplication once you find your model. So it runs fast. So I'll give you another minute or so. Is there anyone else with questions?
I've got one that I've always had that you might be able to take a stab at. Are you familiar with Jean-Remy King's back-to-back?
Yeah.
How does it differ to CCA, from CCA?
I mean, the concept is similar, right?
Yeah.
But I think this is methodologically more direct, because that's what you're doing this directly rather than doing a back-to-back regression. I don't know. I've never seen a direct comparison. The implementation is a bit different now.
Yeah.
So I think this is a more direct way to get what you want. But again, I've never tried it myself, and I've never seen a direct comparison, so I can't comment on that.
What are we talking about here actually? A back-to-back?
I'll put a link to it in the chat. Actually,
that's good.
So Jean-Remy King is a PI. I think he's with Meta, or he was.
As last time I've heard from him, he is part-time, so half-time for working for Meta and half-time working for the CNRS in Paris. That's a couple of years ago, though. I don't know if that's still his status. There is also Lucas Parra's method, Corca, which is more similar to this. And honestly, I remember looking into that, talking with him, but I remember it was very similar. I can't remember the details now, but it's very similar.
I think one difference was about the orthogonality of the components, so that for core, or however you want to call it, it was not. You can interpret the components physiologically, which I think you couldn't in this one, if I'm remember correctly.
Yeah, I mean, the thing is, maybe that's more direct. You can still do it here in a Lance way, but it's less direct. So I suppose, thank you, Nate, for the links, and Aaron. So I suppose this method, when I was using it, at least it was especially for decoding. But then you still have the transformation matrices, so you can, you know how you also use DNNs, we'll see it tomorrow. You can also use DNNs and then interpret the DNN by linearize it and whatever. There are ways to do it here as well. Is it the right way? Maybe that's what you want to see. You better do it here straight away. If you want to study the linear transformation, you better fit a linear transformation sometimes. But at the same time, if you fit a cool DNN, you may want to have a way to interpret it as well. So and there are some compromises you need to do, and same thing with CCA. So yeah, all good stuff. So let me jump to the solution very briefly. Same thing. The solution is just very simple. So you just select the time window, as I said before, a lag window. I selected 200 milliseconds, could be anything. I selected 64 PCs just because it's a nice number, and completely arbitrary for now. Alan would tend to go for very small numbers, 8 components, but I'm aware that if the data is very noisy, if the data are very noisy, sorry, the problem is that the very first components are going to capture the low frequency and kind of ignoring the higher frequencies, and it's problematic. So I tend to get more PCs, and let the CCA do the job afterwards. But you have higher risk for overfitting, so it's a trade-off. So for the time lapse and dimensionality reduction for the EEG is the same line as for the stimulus. You just copy and paste, and then you run this thing, and maybe it doesn't work. So for speeding things up, I put a step of 3 here. Sorry if it's not maybe as. Forgot to add this here. So I'm not getting all the time lags. And then I kill this because we don't have enough time. So I'll do the plot for whatever number of subjects I managed to run this on. Oops. And there it is. So this is actually the plot from before. So you get the correlation for the first component, and you get the match versus mismatch. In this case, based on a window of 5 seconds, not 30. So with a window of 5 seconds, you get the correlation, a match versus mismatch of 70%. If you increase this window to 30 seconds, oh no, this was right. Just takes a bit longer for some reason. Yeah. There it is. I'll just show it to you for 2 subjects, maybe. Let's see if those 2. Yeah. So you see that if I use a window that is a bit longer, I go, instead of from 70, I go to an average that will be 80 or something. So it's a bit higher, which makes sense. So you can play with this, and the point of playing with this is that you don't get something that saturates to being too good or too bad. Because if you get something that is always perfect, then you can't compare a model versus the other or anything. So you need something kind of in the middle. Any questions? Hope I haven't lost half of the crowd.
Yeah, actually, I have a question. So, I think in the code right now we're just using the first CC, right, to do the match versus mismatch classification. So I was just wondering, what would be the strategies be if you were to like use multiple CCs? Like, what would the optimal strategies be for combining multiple CCs?
Yeah, I mean, you can do a sort of how do you say?
LDA.
Sorry.
Like an LDA, like a simple linear classifier, maybe on the CCs.
Well, the way I do it is a simple. Yeah, I mean, I do accounting. So how is it the best? The one that gets more winning. So you do it on the first CCA, you do it on the first CC, on the third CC, and maybe 2 out of 3 said that this was the right one. And so and this has a name, I can't remember now.
Voting mechanism, like voting scheme.
Yeah, exactly. So you can I think I do that. There are other ways as well. You could actually fit a model. I just didn't want to add another layer of model. But absolutely, yes. And the other question is how many components are meaningful. So you can actually study the match versus mismatch for individual components on your validation set, and then you use just those for your test set. Now the third part, which is basically the last part, the last to do for you. And I'm sorry we're going over time. Now the last to do for you. Now the next step, we said that we're using this time shift at the EEG, we're using this time shift at the stimulus. Now we are adding also the shifts between the stimulus and the EEG in general. There is a specific reason for doing that. Sorry?
Is it like a global shift to both the streams?
Yes, it is a global shift. Now there is a reason to do that. We don't want to be redundant, but there is a good reason for doing that. This is all the same code from before, more or less. Of course, one thing you can try to do is to change these parameters and see what happens. Change the number of components, change the window size, try to understand what's going on. So that's your to do for when you're at home. Let's say, well, you're at home, but when you're in your own time. But here we go back to what we were doing before, and I added another line. So one way is to do a shift, so to use time lags. The other way is to use instead modulations of the envelope. So this is something that comes from a number of people, but for example, I learned it from Shihab Sharma and from Usha Goswami as well, separately. Usha Goswami, because she's interested in rhythms of perception or rhythm of speech. And so basically you take your envelope and you just filter it. You filter it, in slower rhythms, in faster rhythms, and that gives you some modulation rates of the envelope. So mind, you're not filtering the speech. The speech is already, you already got the envelope here. So you're filtering the envelope in the original sampling rate maybe. So you're filtering, and you're getting these modulation vectors. And that's what this thing is doing, really. If you look inside this function, it's a smoothing. There is this function that Alan wrote that is taking your stimulus and is just running many different smoothing functions, which is one way to do a sort of a filtering that just gives you basically progressively slower signals that represents the various rates of the envelope. And so that sometimes is better than doing time lags. And so what I use in some cases is that I have maybe time lags in one dimension, on the EEG dimension, maybe, and then I used smoothing filters on the envelope dimension. What Alan called CCA3 in his paper, he was using smoothing filters both on the stimulus and the EEG, no time lags. And then the shift makes sense because the shift is finding, there are no more time lags. So using the shift is finding the optimal latency between the two. So I like using lags and shifts, but it really depends. I don't have a precise answer on what is good. It's really a rule of thumb sort of thing for the moment. So your to do for now, if you open tutorial part 3, is to, let me see, is that the only to do? Let me see if this runs. Is to try the different options on maybe one subject and have a look at the result. Now, I changed the plot here in a way that you can see straight away the result for that particular subject without waiting for running this for all subjects. So let me see, it's going to plot it now. So this is the result for one subject where it's messy, it's terrible, as you can see. And this is actually not good at all. And the match versus mismatch is around 50%. So it's completely random. So this is not good. So I suppose your task is to figure out why this is not good. So there is something in these parameters that is just not good. Check the script, this section from top to bottom, because there are parameters here that may not make sense. So there is one parameter wrong. And I'll tell you the parameters again. One parameter was the shifts range. The other was the number of PCs. The other is the window size of match versus mismatch, number of components match versus mismatch, number of time lags, and whether you use the filters, modulation filters, or the shifts. So play around with that for 2 minutes. Then we'll talk again in 2 minutes, and then we try to close it at 8:30.
Can I ask a question?
Yeah.
I totally understand what Alan was doing in his CCA3 model, like trying to replace lags with the outputs of the filter banks. So is there any guidelines or some sort of a best practice approach for how do you come up with these filter banks, or how do you design these filter banks?
Yeah, I mean, he talks about that in his paper, all right. Sorry, I got confused because we have a nice organizers chat going on, and it's really exciting but distracting. So he talks about that in his paper, but there wasn't a good reason, let's say, that clearly said, okay, this is better than the other. So honestly, it's a tricky choice. Computationally, on the data set that we had tried it in 2018, I think it was, using these ones, the modulation filters was the best thing. But consider that inside here, we are also doing, we're possibly, I won't go into details, but basically, it's an approximation of a filter bank, right? And if you get the right shifts, it's just going to work better not because it's capturing more information, but because it's capturing the same information, but with less dimensions.
Exactly.
So it just fits better. There is less risk for overfitting. But that is just my intuition. I don't know if there is a precise answer to your question there.
Yeah, I think it's like more like changing the basis that we operate on, just by going from time lags to the filter outputs, like changing the basis altogether and then looking into those. So
it's also related to the nature of EEG, right? Because if you think about also ERPs in general, the early responses are fast, time resolve fast. Then the longer the latency, the slower the response is, in part because there is more uncertainty in their timing. But at the same time, it is in the data anyway. So we see it in ERPs and things. So these modulation filters are capturing these progressively slower. So a progressively slower response can actually be a longer latency response. So there is a theoretical concept there, but honestly, we could stay here talking about it for the night, and we wouldn't come up with a simple answer to it. But there is a number of reasons. That's my point.
that's good.
Anyone succeeded in figuring out the mistake?
I think so.
Wait for 3 seconds then, Aaron. Let's see if someone else come up with the answer.
I won't spoil it for anyone.
Let's see if someone comes up with the answer. You can also reduce the number of shifts if you, and also reduce the downsampling frequency if you want to make this faster. And just remember that generally, if it works for TRFs, it works also for CCA. It's just that CCA works a bit better. And it still gives you the flexibility of doing multivariate models, by the way. We're not doing them now, but you could combine phonemes, word stuff, and everything here. And I did that in my 2019 neuroimage paper on phonotactics. So you can do that. Anyone else with the answer? Sarah, Amir, Joshua, Bonnie? Nate? I'll wait another minute, and then I'll give you the answer and we'll close the session because we are really over time. I'll just give you a description of the final part, which you can do separately. Oh, Nate, I saw now your text there, the chat. All right, and before I give you the solution, I mean, you understand that the point here is, okay, now we have a CCA code that, okay, CCA is complicated, but if you wanted to run CCA, this runs on the CND structure. So this is, you can just take the same thing from before, from the other scripts, and you just run it on the same data structure. There is going to be more. We're going to add other algorithms and other things later on, you know. It's just going to take time. So if I remember correctly, this is the main issue. So basically, if you look here, we had just one PC. Is that the answer we're going to give, Aaron?
That I found changed it the most drastically, but also doing the modulations of EEG plus PCA or shifts of EEG plus PCA does give a little bit of extra juice. So adding the shifts does give you a little bit of, but mostly the PCs. That's
great. So I mean, if you just get one PC, it's just one-dimensional thing. You go back to the TRF and really you're taking whatever has most variance, which may not be most relevant. So you need to keep at least 4 or 8 PCs to get something good. I mean, depends, I suppose. So you'll have the solution anyway. I'll fix the thing on the website so that you get also a solution and tutorial scripts. So if you want to go back and redo things, I think it's a good exercise for you to figure it out, because these are the parameters that you struggle with when you run CCA. The main thing is here on part 4, this is not really a tutorial, it's more the final script, which I'm actually going to share as well as example 4. It's basically the same thing. So you're going to have example 1, 2, and 3, you know, TRF, 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 and then CCA. So example 4 is what you can use as blueprint. Now in this case, the way I do here is for number of components for the match versus mismatch, I select 0, which means all components, which should be the case, if properly tuned anyway. I select 64 components, which is you know, maybe too much, but it works. window size of 5, because if you get a window size of 30, you get very high correlations. So I wanted to lower that a bit, very high classification, sorry. And then I ran the shifts for the stimulus and the filters for the EEG, but you could do the opposite. You know, you could do the opposite there, but they ran one for one and one for the other. And then the CCA cross-val. For the plot, so you remember what, this is the last thing I'll tell you. Remember what Liberty was saying about plotting the TRFs with negative lags or with positive lags, and different people do different things. Okay, with CCA, you have an extra order of complexity because you have 2 transformations and 2 time shifts potentially. So, you know, do you plot them? So this is what Liberty is doing. She's putting a minus on her plot compared to what I usually do with TRFs. It's the same, it's compatible. It just depends how you look at it. I put a minus here to keep things as I usually do. If you remove the minus, it's what Liberty usually looks at. But if you launch this thing, you're going to get the figure I showed really at the end of the slides. So match versus mismatch for each subject. And so here really you can go and then compare whether this is working better or worse than TRFs. But you need to be really careful about tuning. So this code is not quite doing the nested loop cross-validation that Nate was showing, but it is set up to being extended to do that. So you do the cross-validation on the training portion. So the training portion includes training and evaluation, and that's what is launched here. And then you can, you know, if you can, in this case, you're removing the test trial from the training set, and you can launch your evaluation on the test trial. And that would be the way to do it, like Nate showed. But again, understand how things work first, and then you can properly tune it. So this is what's running now for subject 1, and you can see, you know, how the shift, you know, shift of 500, 600 milliseconds is most meaningful here. And oh, I didn't flip this. Anyway, I forgot to flip this, sorry. Yeah, I should have flipped this as well. But basically, you're going to see your classification here and your correlation here, if that makes sense. Is there a question in the chat? No. Funny story, I saw the NPC issue in the code and I thought my code might have been outdated. So Nate thought it was wrong code, but it was actually the solution. Well done, Nate. Any questions before we leave, before we close it?
Yeah, I think I still have a very naive question. So if you have time lags on both sides of the arrow, let's say I shift the one, let's say plus 30 and the other one plus 30 as well. Like, wouldn't it be the same as if I would have plus 60 in the one and 0 in the other? Like, do you get my question?
Not if you run PCA. That's the answer.
Okay.
Also, CCA is a component analysis. So if you run lots of lags in one dimension, so imagine you have the envelope here and 64 channels of EEG. You run the lags on the EEG, and so you have 600 dimensions. If you run the CCA, it's not going to work because you just get one CC. So you could run 60 lags on the envelope. But then do you run the PCA? Do you not run the PCA? So if you run the PCA, it's not going to be the same. So generally, you need this kind of duality. You need to think about both. The other thing is that you can potentially go here and, as I said before, you project for example, the EEG to the CC domain after you fit this model, and then you can remove you can just keep the first 3 components and you project it back. To do that, though, you need to have, very important, approximately equal dimensionality on stimulus and EEG. So if you have 64 dimension on the stimulus, you need 64 dimension on the EEG, you go onto a space that is about 64 dimensions. It could be a bit less, depending on the rank. And then you can project back and forth. But if you project onto a space that doesn't have enough dimensions, you're going to compress your data and you're going to lose. It's a lossy compression. If it has the same number of dimensions, it's a lossless compression. So you don't lose. You can go back and forth and just remove what is meaningless to you. And actually I have a paper on that. Let me do some self-advertisement. I hate self-advertisement. No, I'm lying. I love it. No, let me see. Post. There it is. Now it's a funky one because I usually study speech, but this one was on a different project. It was on driving. People were driving a simulator, a car simulator, and they had all of these EMG accelerometers and everything. And so I use CCA here as a way to denoise the EEG from all those sensors that were, this was the simulator. And what you do basically is that, you denoise your EEG from all those, you remove the EOG, you remove the EMG, you remove the accelerometer. It's similar to ICA, but you're removing what you're telling the model to remove. So it is selective to what you want to remove. And then you check, I remove that, I remove the accelerometers. Is the result still significant? Yes, it is, but it's terrible compared to before. Still significant, but terrible. So you can use CCA for that. I just put this in the chat. It's not about speech, but the method was covering that. And we got a patent out of that, so. All right, we started with 25 people in the room, while there were like 40 in the other room, and now we have 15. So thanks a million for sticking with us. Do you have any final questions?
I just have one final question about the way PCA is applied as a pre-processing step, because I personally feel that you should apply PCA on the train set and use the same PCA on the test set. But what I've seen the community do is that they apply PCA to the whole set as a pre-processing step, and I'm not really sure if that's a good practice.
It always depends on what you want to do. So there are some cases where there is no problem in doing that. One could argue, and Alan himself does that, arguing that if you launch PCA on the whole data set, you're not biasing your data set toward any of the particular questions that you're studying. Now, the issue is that if you're doing cherry picking there, or if you're running everything until you find a good result, that's an issue. I agree with you. The safest way is just you run it on the training set and then you apply the same transform to the test set, which I don't expect to be too different. But at the same time, if your transform doesn't have anything of your test metric, which in this case is correlation, then it's fine. But again, I can't give you, don't quote me on that. So it depends on what you are testing. So be careful.
Thank you. Yeah.
I just want to jump in. I agree with Vishal, honestly. So the reason PCA applied to the full data set probably wouldn't make a huge difference is because you're focusing on the maximizing variance, which isn't necessarily the thing that will help you like accentuate modeling. But you never know. Like it could bias it in ways you don't expect. So I agree that you should run PCA on training and then reapply that transformation. Yeah, nice one.